kind of an evolution from simple to complex. But the Darwinian theory does not really explain why it becomes more complex. It explains why things evolve. It explains why things become better and better adapted to their environment. But in principle, you can be adapted by being a very simple thing like a virus or a bacterium. You can adapt it by being a very complex organism, such as a human or like a society. So now we need to explain where does that complexity come from. Evolution gives us a mechanism why things change in a particular direction, but not a priori why that direction is towards complexity. And why of Darwin starts from certain units. In the case of Darwin, these were individual organisms. In the case of the new neo-Darwinian theory, the units are genes. In some other cases, the units may be mean. These variations succeed, they are selected. Some of them fail, they are eliminated. But if we want to explain complexity, we need more than individual units, we need wholes. So that's what I'm now going to explain in the next chapter. I'll start with one chapter that is still relatively classical. That's a chapter on self-organization and chaos. Now, self-organization, it's a phenomenon that we all know. We do find in nature certain shapes that have self-organized. For example, this shape of a crystal, of a snow crystal. Here are some examples that I took myself. It dries up, but it doesn't dry up evenly. No, it forms this kind of very complex pattern of cracks. That's another example of a photo I took. These are ice floes that have formed on a car that was in the street when it was freezing. You see they have very complex, beautiful, orderly shapes. Now, we can't explain that to some kind of a natural selection. It's not that as if there were lots of different cars with lots of different formations of ice crystals and only the ice crystals that had this particular shape would survive. It doesn't work like that. So we need to go deeper. We need to go not at the level of the whole, but at the different parts and see how these parts fit together. So that's another example where you see two types of self-organization. Here you see the cracks in the mud, and here you see bubbles that have formed that are all these. Roughly speaking, the second law of thermodynamics says order tends to dissipate. Things tend to become more disorderly. If you leave something apart, on its own, it will degrade. We will see in nature, you might say that things tend to degrade. We know that if you don't clean up your room, it's not going to clean itself up, it's going to get more and more dirty. There will be dust that's accumulating. Things do not generally order themselves. So this second law says the entropy, which is this kind of a measure of disorder, tends to increase. So how can something that is ordered then appear? Now, there is one person who has gotten a Nobel Prize for studying that question, Heylighen, because not only he got a Nobel Prize winner, and he also had a very big influence on this new worldview, he was also somebody outside of the road here. He created a school that's known as the Brussels School of Thermodynamics. Prigogine developed a very interesting concept called the dissipative structure. The dissipative structure, we'll speak about it later, is a structure that dissipates entropy. So the second law of thermodynamics says entropy always is formed. So there will always be disordered form. But what Prigogine says, well, it's not a problem if the system can somehow export that entropy system, then in principle the system can order itself. So that was a solution. So a dissipative structure is a structure that organizes itself, because we use the term self-organization, by exporting the entropy. The entropy, the disorder is turned out of the system, and that allows the system to organize itself. So I'll give you the simplest possible example of self-organization to show you the principle. Yeah. Okay. So let's first make the definition. A common definition of self-organization is global order emerging out of local interactions. Local, lots of small parts like individual molecules. These molecules interact locally, the one with the other, and the whole globally orders itself. It has some kind of a coherence, it develops some kind of a structure, some kind of an organization, and it does that spontaneously. What does it mean spontaneously? It means that there is no agent that is telling the system how it should organize itself. So we saw that one of the arguments for the religious, it must have been designed by somebody. Some intelligent being must have thought about how to put all these things in the right order. And like things like organisms, well, the only thing we can think of is God has designed these things. Now, self-organization says, no, you don't need a designer. There is not an agent somewhere that has. That is an example of the chemical reactions that were studied by Prigozhin and his group. The Belousov-Zabotinsky reaction. You don't need to remember the name, but it's a chemical reaction that tends to form these kind of spiral waves, and that tends to change color in time. It's sometimes also called a chemical clock, in the sense that you can have a chemical mixture that is red 1 minute, then blue the next minute, then again red, then again blue, then again red. It changes colors. There is no intelligent agent that is telling the system how to organize itself. So let's try to explain that using an extremely simple example. Well, that's another example of an ice, and that's the example of a global magnetic field. Now, that magnet typically consists of molecules, small parts, that each have a magnetic field on their own. Now, normally, these magnetic molecules, they are disordered. They're pointing in different directions. In some cases, they align themselves. And when they are aligned, instead of the different magnetic fields annihilating each other, they reinforce each other. They all point in the same direction. So how could that happen? So one way that it could happen is to an external influence. You can do that experiment if you have a needle or a pin that meets a piece of iron, and you glide with a magnet along that pin. The pin will become magnetic. You can test that. If with that pin you then touch another pin, you will see that the second pin continues, hangs on the first pin. I once did that experiment when I was at university. I hung that pin somewhere on a wall in my room, and years later it was still hanging there. So I had magnetized that pin. But in this case, the magnetization was obvious. I put an external magnetic field, and then that external magnetic field was strong enough to make all these little magnets all align themselves and point in the same direction. But now we want to understand how could it happen spontaneously. And now we can go back to some of these ideas of evolution, because in a material, the molecules are not completely stable, they move. If something has a temperature higher than the absolute zero, that means that there are so-called thermal fluctuations. That means the molecules in the material move, which means that these things, they go in different directions. And so this one can turn like this, or can turn like this. So they all move. So that by chance, this, which means that that photon, if it's now moving also randomly, will tend to also join in that same direction. It tends to align. And the more that have joined this alignment, the bigger the influence on the rest. So what you see is that the alignment kind of propagates. It's like a wave that spreads. if in this chaotic neighbors are not aligned, the bigger the patch becomes, the stronger its effect of the rest, and so the whole thing may get aligned. Now, I'm giving you a very simple scenario, play a role, but we're not going to go into the physical detail. That is the principle. The principle is they start randomly, very low, but a selection of a direction of alignment, so that if two or more are aligned, they kind of reinforce each other, and the more that reinforce each other, the bigger the influence, and the more they saw that there was these local interactions. Locally, these molecules, they feel the effects of their neighbors, but they don't feel what's going on far away. They only interact locally. But by locally aligning themselves, the alignment grows, it propagates, it's a very simple principle. And now in this case, the alignment is obvious because there's only one direction in which they can be aligned. But if you have more complicated cases like here, well, there will be different forces so that the alignment is something from others. But generally speaking, by alignment, I mean two elements getting into a relationship, reinforcing each other. When they are pointing in opposite direction, they are opposing each other, they are in friction, they are kind of in conflict. The moment they find a way to avoid a conflict, they are more likely to stay in that. So there's a kind of a local selection of alignment or synergy. So that was a lake in which there were sticks of reeds that had just fallen into the water, and if it's windy and they move, they will tend to continue moving together. So here you see this spontaneous alignment. Go to a bit more complicated example, an example that was also studied by Prigogine. It's called Bénard convection. Convection is you have a liquid and you can do the 2-3 millimeters of oil and you heat. But let's look at a simpler case. In a round pan, you would have a long, narrow pan, a rectangular pan. You're more likely to get, instead of hexagons, you're having. So what's happening? Here is a liquid. The bottom is heated. The surface is cool. Here, the liquid cools down. Here, the liquid is heated up. Now, hot liquid is lighter than cold liquid, so hot liquid tends to bubble up, to flow up. Cold liquid tends to go down, but that creates a here things want to move up, there they want to move down, they're in each other's way. What needs to happen is that these water or these liquid molecules need to coordinate their movement. And how can they coordinate? For example, by all going up here and all going down there. But those that go up here, they come to the surface where it's cooler, so they start cooling down. Once they are cooled down, they want to go down again. They go down again, but then they come to the bottom where they get heated up, and then they have to move up again. So what you get is you get a kind of a roll of liquids. And the example of the hexagons, what you see is that the liquid is coming up in the middle of the hexagon and it's going down on the border of the hexagon. But let's speak about the example here where we're just seeing it in one dimension. Going up in one direction, moving to the other side, going down, moving back, going up. So you have a roll, and if you have a roll here that's going clockwise, then the roll here necessarily needs to go counterclockwise, because otherwise there's friction. Here again it needs to go counterclockwise, the next one will again go clockwise, etc. So the whole thing segments itself into a number of parallel rolls of about the same length. Let's see so in a little bit more detail. So that's another depiction. So the red arrows means heat being added. hot liquid goes up, it gives away some of its heat at the surface, it cools down, it becomes blue, it goes up again. So you see that's the separation in rolls. Here, that's a kind of Heylighen. And I think we may even have a movie, if it wants to work. See, the red is the hot liquid. It first a little bit kind of experimenting, stabilize so that there is this nice roll here and a nice roll there, moving in opposite directions. So let's go it again, maybe. Come on, that's not what I want. Okay, I mean, we've seen enough. Let's draw some general conclusions from these two examples. So we saw one example, magnetization. All the different arrows go into the same direction. That's static self-organization. It's like a crystal. The molecules arrange themselves in regular distances, in regular order. That's the static version of self-organization. The second one, that was the Benard convection. There it's done because you have a process. The thing continues to run. And that is exactly what Prigogine called a dissipative structure. A dissipative structure is a system that is constantly moving, and while it's moving, it's dissipating. And in the case of an air convection, what is being dissipated is the energy which you add from the bottom. You're heating from the bottom, and then the heat goes into the air above the liquid. So you're dissipating the heat by that process. But while you're dissipating, which is a process that generates an entropy, you are creating a structure, and that structure keeps itself alive. That structure remains active. That's what Prigogine called a dissipative structure. Why is that such an important concept, a dissipative structure? Because a dissipative structure is something between life and non-life. The crystal, we all agree, it's that. It's rigid, it doesn't move, it's fixed. It's like a stone. A living being, constantly things are going on inside a living being. A kind of an intermediate case, a dissipative structure. Other examples of dissipative structures, a river, a whirlwind, a hurricane, a flame. All of these are things that are constantly moving, and they can only move because there is some input of energy. That means some input of things that have low entropy, and the output is something that has more entropy. So a river continues flowing because the heat of the sun will heat the ocean. The ocean will evaporate, the water will rain down in the catchment area of the river, and it will flow back to the sea. So it's this hydroelectric structure. It's organized, it's moving, it's active, but it's not alive. It's a step in between life and non-life. Some other aspects of these self-organized structures is that structure is what is called distributed. The organization is not localized. There is not any of those little magnets that is the boss, that is the central director. All of the little magnets are aligned with each other, which means that globally, collectively, they form a certain order. And that collective order, you also see in things like, for example, we will see later examples of swarms of birds, beehives, ant nests. All of these are collective organizations, I mean, lots of little elements which together collaborate in such a way that they form this global order. There is an emergent order that is not at the level of any of the elements, but at the level of the whole. That has some advantages. If the order is distributed over all the elements, it means you don't need any particular element. It means if, let's say, I would have this magnet and it would consist of billions of these little magnets all pointing in the same direction, and I will drop the magnet, and because of the shock, many of these magnets would lose their alignment, they would move in a random direction. It wouldn't really affect the magnet because there would be enough of them that are still aligned to pull the others back in. So that is a characteristic of self-organizing systems that's called robustness. They are robust. That means they can withstand shocks. All kind of random perturbations, typically the self-organizing system will mend them on its own, because the only way to destroy such a collective order is that you need to move all of them out of alignment. So if you just move 10% of them out of alignment, the other 90% will make sure that they get back into place. And that is a principle that we see also in much more complex self-organizing systems. For example, the brain is a self-organizing system. There is not a single part in the brain that tells what the other parts what they should do. The brain is a network of neurons. These neurons interact locally. They send electrical signals the one to the others. Out of these trillions of electrical signals, something like, let's say, consciousness emerges, but that does not depend on any particular neuron. People who undergo brain surgery, for example, because they have to remove a tumor, these people may temporarily lose some of their abilities. If, for example, they need to take away a tumor that is close to the center where language is, these people may have difficulty finding words, but after a while they will recover that ability. So there isn't really a part of the brain that is essential in the sense that it is necessary for the whole to function. Different parts of the brain can make up the one for the other, and that's a typical characteristic of all self-organizing systems. Because the order is global, local damage typically doesn't have much effect. Yeah.
How does the fact that the brainstem tends to be, like, if you damage the brainstem, the brain cannot replace that part, and usually the animal dies fit into it?
Well, of course, if you damage enough, it will always die. And some parts of the brain, like the brain stem, which is really the part where you connect to the rest of the body, yeah, then it becomes very difficult. But especially the higher parts of the brain, the so-called neocortex, is quite redundant. That means there are lots of things that are doing more or less the same. So if you take out some, the others will compensate. So another way to say this is called redundancy. It means that you have many things that are doing more or less the same, like these different magnets, they're pointing in the same direction. So if you take some out, it doesn't make such a big deal. Now we come to another important concept, the concept of non-linearity. Non-linearity is a concept you will hear a lot whenever you read about complex systems, and it's a bit of a silly concept because it basically says what it is not. So non-linearity is something that is not linear. So in order to understand what's non-linearity, you first need to understand what's linearity. So let's explain it with some elementary mathematics. Suppose you have a function of some number, let's say a function of a. That function may be something, for example, you calculate the force exerted by something of magnitude a. Now, a linear function, by definition, is a function that if you apply to a sum a plus b, the result is the sum of applying the function to each of the things separately. That is a definition of linearity. That also means if you apply f to a plus a, you get f of a plus f of a is 2 f of a. So f of 2a is equal to 2f of a. And you can generalize that f of a times something is that something times f of a. So if we take a as the input or the cause, and f of a as the effect, the output, then what you can say is, what it means is the effect is proportional to the cause. Linearity means proportionality. If I push a car and I push it twice as fast, twice as hard, it will move twice as fast. If I have a paper factory that takes wood pulp and produces paper, and I put in twice as much wood pulp, there will be twice as much paper coming out. If I put in 10 times as much wood pulp, 10 times as much paper will come out. That is linearity. It's proportionality between what you start with and what's the outcome. Proportionality between the cause and the effect. So it's a very simple concept, and it's a very intuitive concept. Lots of the processes we know are linear. The effects are proportional to the causes. So what is the non-linearity? That the effects are no longer proportional to the causes. No longer proportional, that means they could either be much bigger or they could be much smaller. Suppose that you would have some magical machine. If you put in twice as much wood pulp, it produces 10 times as much paper. That would be a non-linear machine. But it could also be the opposite. You put in twice as much wood pulp, and you only get 1.5 times as much paper. That's also non-linear, but in the opposite direction. So now, why is this non-linearity so important? Because the kind of processes that we see in self-organization are typically non-linear. They are non-proportional. We saw that with the magnets. I said you start with 3 or 4 magnets aligning, because now they are stronger together than alone. They will tend to align their neighbors, which will tend to align their neighbors until the whole thing is aligned. That's clearly non-proportional. I start with a very small cause, a few of the magnets align themselves, and all of them get aligned. That's the example of non-linearity where the effects are much bigger than the causes. You can also have the opposite. The effects are much smaller than the causes. Now, suppose that all of them have gotten aligned. I told you if I drop that magnet and let's say that 10% of the magnets are thrown out of alignment, the other 90% will pull them back. What does it mean? I have a very big cause. I shake 10% of them out of alignment, and I get 0 results. They all become aligned again. So self-organizing systems, they typically start with growing effects, more effect than cause, and then once they have finished their self-organization, you get the opposite. It's what we will call a little bit later a positive feedback and a negative feedback. The positive feedback is when the cause is amplified. You get a big effect for a small cause. The negative feedback is when the cause is suppressed. You have a big cause and you have a small effect. Yeah.
Is that still predictable?
That's just what we will come to now. It is still predictable up to a point. So now we come to this other notion, chaos, or better, deterministic chaos. This is popularly known as the butterfly effect. Where does this idea of the butterfly effect come from? If you describe the weather as a system where differences in pressure and temperature in different regions produce winds that move heat from one region to the other, in principle, in theory, you could describe the weather as very complicated mathematical system of equation that says how future temperatures, pressures, and wind direction depend on present temperature, pressures, and wind direction. Now, that mathematical system turns out is nonlinear. That means that small causes can lead to big effects, and theoretically, a small cause could be a butterfly that flaps its wings, that creates a small difference in air pressure, that creates a very small difference in wind direction. In principle, that very small effect of that butterfly could, if you wait long enough, 6 months later, create a hurricane in some different part of the world. So, typical example they give is a butterfly in Tokyo flaps its wings, and 6 months later it creates a hurricane in New York. That is the weather. The weather is a nonlinear system. Or it's called sometimes also a chaotic system. A chaotic system means a system where very small differences can lead to very big differences at the end. Now, the better term for that, instead of the butterfly effect, is called sensitive dependence on initial conditions. So the kind of mathematical models that physicists and others use when they try to predict things, you start with an initial state. You describe, let's say, how temperature, pressure, wind, etc. are at this moment. That's your initial condition. And then you extrapolate. You see how is it going to evolve, how is it going to change over time. Now, in the case of the weather, you will find that the result, that means what the weather will be 6 months from now, is sensitively dependent on these initial conditions. So this initial condition where the butterfly flapped its wing, and another initial condition in which the butterfly did not flap its wing, they may lead to very different outcomes. The one may result in a hurricane, the other not in a hurricane. So that is this idea of sensitive dependent on initial conditions. If you would draw it, if you would have one condition here, the butterfly flapping its wing, and one condition there, the butterfly not flapping its wing, the two conditions are very close together because they're almost the same. But the one leads to one outcome, the other leads to a completely different outcome. And now we come to the question of predictability. This is called deterministic chaos. It's deterministic because we kind of assume that those equations that would describe the weather give you one exact result. For each initial condition, there is just one possible trajectory. It's an assumption. It's not an assumption that I would say is useful in practice, but it's an assumption. But even if you can exactly calculate the trajectory starting from this condition, but then it turns out that if you make the tiniest mistake in your measurement of this initial condition, and then the result is that, it means that in practice you can't predict. That's why we can predict the weather up to a few weeks, but nobody can predict the weather 6 months in advance. So that's what the sensitive dependence on initial conditions means. It means that the determinism that Newton assumed, even if you stick to that determinism and you stick to the idea, all the things that happen in nature are determined by equations, and these equations have only one single solution for every initial state, even then you can't predict because you cannot measure so precisely that you would know every butterfly that flaps its wings. There are always so many tiny influences, tiny fluctuations in anything that you can never measure precisely what the initial state is. So even if the dynamics would be deterministic, you cannot predict. So deterministic chaos was one of the big evolutions that kind of put into doubt the whole Newtonian worldview. So the Newtonian worldview, well, we assume that things are deterministic because we want to be able to predict, but now it says, well, even if you assume that they're deterministic, you can't predict. Yeah, that makes the whole Newtonian worldview much less useful. There's another interesting concept that is to the example of the Bénard convection. So you have a liquid, you heat it from below. At a certain moment, you see that the liquid starts moving up in one spot and moving down in the other spot. So we see something like this. But is that the only way that a liquid could self-organize? No. In principle, it could just as well have done the opposite. It could have gone up in this place and gone down in that place. It means that if you want to find a solution for the liquid to self-organize, actually there's more than one solution. And one way that is described mathematically is, let's assume that we measure the difference in temperature between the bottom and the top. So if there is no difference in temperature, there's no movement, nothing happens. And then you gradually increase the temperature difference. That means you start heating more and more at the bottom. Initially, nothing happens. At a certain moment, the liquid that gets heated below starts pushing to move up, and the system needs to self-organize by moving like this or moving like that, but it has two options. It can move up or it can move down. So the bifurcation means that if you increase this temperature difference, that means if you bring the system farther from the equilibrium state where nothing happens, it needs to make a choice. And even if you have a deterministic model, again, you don't know which of the two options it will choose. And what Prigogine argued was that, well, self-organization starts from a fluctuation. That means there's always some random movement in your liquid. And it's sufficient that a few more molecules are moving up in one spot, that whole spot will start moving up. But it could just as well have happened that in that same spot, there were just a few more molecules going down, and then it would have started moving in the opposite direction. So what Prigogine, among others, was looking at was these kind of systems where you bring the system farther away from equilibrium. Farther from equilibrium, that means that you push more energy into the system. That typically makes the system more non-linear. That means it will react more strongly because it has more energy. And at a certain moment, typically, it comes to a situation where it needs to start moving in a different way than it did before. But it typically has more than one option. And if you go on, you typically see that one bifurcation, that means a splitting of the two possible options, is followed by another bifurcation, is followed by another bifurcation. And if you go far enough, the whole thing becomes chaotic, turbulent. So if you continue heating up that liquid, after a while it becomes like one boiling liquid with all things moving in all kinds of different directions.
But Francis, is this bifurcation also like a reduction of complexity? Because at each kind of stage, it's sort of reduced to only two possibilities, right? Like either it spins clockwise or it spins anti-clockwise.
Well, the bifurcation in the literal sense that there are only two, that's idealistic. I mean, in some cases, like in the case of the Bénard convection, there are indeed only two options, but in many cases there are more than two, or there can be three, or there can be 100. So there are some nice mathematical models that look like that, but in reality there are many more options. So bifurcation it's nowadays bifurcation is kind of a term to say something changes drastically. The system starts behaving differently.
Same as a tipping point.
It's kind of like a tipping point, yeah. So let's give some more examples of these kind of nonlinear systems. A very simple example would be if I put this standing on its tip, in theory it could stay in equilibrium. In practice it will fall, but in which direction will it fall? If I put the pencil on its tip, you know that the pencil will fall, but you can't say where it will fall. It can fall this way, this way, this way, this way. It's not a bifurcation. There are an infinite number of directions in which it could fall. That's typically a kind of an unstable system that cannot stay in the position where it is. But what will be the next position in a nonlinear system? The slightest fluctuation, a few more air molecules bumping against your pencil from one side and from the other will make it topple here, or make it topple there, or will make it topple there. So that is typically of these nonlinear systems. The tiniest microscopic invisible effects may push it in one direction or another, yes.
And so that chaos, I think you just used the word turbulence.
Mm-hmm.
It's very akin to the air molecules in your pencil that...
No, turbulence is more than the air molecules. That is, let's say, traditional disorder. That means that statistically it's predictable. Turbulence is more complicated than that. Turbulence, you can have both small and big effects, but you can't say which one. Well, with the air molecules, it's all small. All these molecules make small movements. Tiny movements, they may be enough to make your pencil fall, but at the level of the air itself, nothing much happens. On the other hand, if I would be under a waterfall or in the rapids of a river, there would constantly be all kinds of waves and vortices and things moving. That's turbulence. So turbulence is different from the kind of simple disorder that you find in air. Okay, that's a good moment to have a 10 minutes break, and then we'll start with the next chapter.
Turbulence is the way that bifurcations after some time becomes chaos.
Yeah.
Okay. So the turbulence is dependent on the bifurcation, the existence.
It's typically the result of several bifurcations. At a certain moment, a bifurcation needed to increase the number of possibilities.
Yeah.
But turbulence is when the number of possibilities becomes infinite. It means it's the number of
It tends
solutions
towards
are.
it. Okay. And then this reminds me also of the sensitive dependence on initial conditions. Reminds me of the multiple pendulum. Hamiltonian, and I don't know if that's used here.
Well, I'm not going to go into the Hamiltonians. That gets very complicated, right? For some formalisms use Hamiltonian, but you don't need it generally for entropy.
Okay.
Entropy is simpler than the Hamiltonian.
Okay, perfect.
We will discuss entropy later. Entropy is pretty simple.
Yeah,
These kind of equations get complicated.
Yeah.
Unpredictability in stage of non-linearity, like self-organizing structuring which way it goes, like or this. And what it makes it a specific structure, like that it's not in between static non-alignment and like fluid alignment.
No, the distributive structure is ordered because its behavior is pretty regular. Like a river, it flows typically with one particular direction at a one particular pace. So most dissipative structures are pretty stable. So you need initially to organization, you need some activity, but once the activity self-organizes, it stabilizes itself typically.
So it has nothing to do with the way in which it organizes itself.
Well, the unpredictability is typically at the stage when the self-organization starts. When the self-organization ends, it stabilizes itself. But the unpredictability is that you don't know how it will self-organize. I gave the example here where you have two solutions. In general, you have an infinite number of solutions. Like, for example, with a magnet, it could all point like this, or it could point like this, or it could point like that. Each of these is a possible solution, and you can't predict which one. But once it's there, then you can predict very well how they will point because then they all stay in the same direction.
And is it the fact that they stay in the same direction that makes it fit the similar structure, or is it the apparent illusion of choice in the self-organization that makes it a similar structure?
No, the distributive structure is defined by the fact that it is a stable structure, that you recognize an order in how the order was created. That's where predictability comes. You don't know which order will come out. Once the order is there, then you can predict it.
Because I thought the fact that the distributive structure was
Idea, the good thing about it is like,
that like points it on a sort of
it's on
maneuverability, that it's not determined as something which is non-alive and fixed.
But it would be nice to, last time I was also working with
alive and movable, and that the different ways of organization
seems to be like super glitchy.
that sort of illusion of choice is what makes it.
You're a legend.
That's
You
not
have
the
a
function. What you're speaking about is more what's called chaos. That you have this kind of, especially living systems tend to be on this in-between and disorder. But for most distributive structures are pretty orderly once they have formed.
Yeah.
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 That's the game theory. So it reminds me of how structure reminds me of how people would interact. They would play game theory after a long time. They would understand that it's better to take the book to route and thus all realign in the same way. Is that an analogy that I can make?
It's an analogy you could make. It's called an evolutionary stable strategy. Evolutionary stable strategy. It means that if lots of different strategies are playing against each other, after a while they stabilize so that particular strategies dominate and stabilize itself. We will discuss that later. Not in a lot of detail, but we will discuss that.
And then there is a last thing. Sorry, it did just interest me a lot. There was a paper that I am reading about anarchy and complexity.
Okay, yeah, you're in the right place. We just had organized a symposium about anarchy and complexity.
Oh,
Yes, my colleague Eva actually was one of the organizers of that. He's applying these things to anarchism.
okay.
Yeah.
Okay, I'm very interested in that, but I was just.
Maybe I should write down his name as if you search
Yes.
him, you will find
Please.
Evo, like evolution.
Yeah.
Bussoniers.
Like
Yes, yes.
Thank you so much.
Or just search for complex anarchism. Complex anarchism symposium.
Okay, thank you.
Just checking. My timetable says that I have this class after this class.
The second class is for the working students.
Yeah, okay.
So it's just the same.
Yeah, okay.
So you don't need to be there.
Okay,
Yeah.
Yeah, but we could only find our, like, the, when we measure, we can't find our velocity electric courses. Just, yes.
But so far it's more separate.
Is it in Dutch? Like Dutch. Okay. Philosophy, when we put it. But I think it's oh, yeah. So it's really interesting. Yeah. Why is it any of this? That isn't how I heard
To reconcile it with the religious ethics. And also interviewed the Dalai Lama. And when I wrote this, they come together, and then the next Dalai Lama will be one like
Oh. Okay, so an exam is in November.
I did it in Dutch without
Horrible.
No, there are Chinese, Russian, Polish, and it's three parts. This one one month also I was thinking of Francis also
No, more like one lesson. The word meme. Day of the week is it?
Someone who's talking about someone who's combined with someone from
Yeah, sure.
but it's better interesting that I was just reminded that in theory I have a second 2-hour lecture after this for the English students. I hope none of them will show up.
Oh yeah, the same again?
Yeah.
Oh, okay.
But I normally for them I do a very quick overview. I go over the whole course in English and all that stuff. Ja, so e-mail of email.
It's so good.
But I think biology is not, so I recognize
Francis,
Yep.
can I ask a question about dissipative structures?
Yeah.
The precise structure that substance takes, is that relating to the efficiency of that structure for releasing energy? Does that make sense?
Yes, there have been attempts to find out which dissipative structures would arise as being those that maximally dissipate entropy. It's called the max entropy principle, but it's controversial. That means it's not really proven that it's always like that, and there are some counterexamples.
It seems intuitive that a whirlpool, the pattern of a whirlpool emerges because it's the most efficient structure to release energy in water.
Yeah. It probably works for simple systems, but once it gets complicated, there is no guarantee that the one you will find will be the most efficient one. Okay, let's start with the next chapter, which is a chapter on systems theory. So now I have basically introduced evolution, which comes from biology, and cell organization, which largely comes from physics and chemistry. But both of these, they're still not yet, they're still kind of reductionistic. In self-organization, we see that kind of global collective structures emerge, but everybody uses these terms emergence, but then when you ask them what does it mean, emergence, lots of scientists will say, well, I can't really explain, it's kind of mysterious, what is emergence? So this concept of emergence is something that is philosophically very interesting because people kind of disagree on whether it is real or whether it's just an illusion. Now, I do believe that emergence is real, but for that, we need some good definitions. So we need a different kind of science, a science that does not start from the elements, the particles or the molecules or the genes, but that looks at the whole as a whole in its own right. So a whole is not just a collection of parts. And this is something that already Aristotle noted. He said that the whole is more than the sum of the parts. It's a nice phrase, but what does it mean? What is there more? So a reductionist scientist would say that's nonsense. It's just a part. If the parts are there, the whole is there. The whole can't have anything that's not in the parts. So what is it that a whole has that the parts do not have? I call that emergent properties. So an emergent property is defined as a property of a whole which you cannot find in the parts, which you cannot reduce to the parts, which you cannot predict starting from the parts. And defined in that way, actually, emergent properties are quite common. There's nothing very mysterious about that. Let's take a very simple example. A car consists of lots of different parts, but put all of these parts and look at these parts and now ask, what is the maximum speed of that car? Obviously, you can't say that. You have to put all these parts together in order to form a car, and then that new whole, the car, will have properties such as maximum speed, fuel consumption, CO2 output. These are properties that do not exist in the parts, and you cannot typically predict what the maximum speed of the car will be before you have put all the parts together. Let's look at some other examples. So one of the classic examples used is in the chemistry. Table salt, what we all put on our food, is a simple molecule. with a formula NaCl, where Na stands for sodium or natrium in Dutch. Cl stands for chlorine. Now, sodium on its own, it's a soft metal that will burn your skin if you would touch it. It's highly reactive. Chlorine is a poisonous gas that was even used in the First World War as a kind of a chemical weapon. So obviously these two things on their own, sodium and chlorine, you really wouldn't want to put them on your food or to inhale them or to come in contact with them. But put the two together into a molecule, sodium chloride, and you get something that we all need, that is part of our body, that is part of our food, that has a number of properties that are completely different from the properties of sodium or chlorine. For example, salt will form white crystals, while the one is a gas and the other one is a metal. Clearly, the whole has properties that are not in the parts. Some of the typical examples of emergent properties: being alive. For a long while, scientists have been working on the assumption that there is a fundamental difference between living matter and dead matter. And they kind of assumed that there was something called the vital force that a living matter had. Nowadays, we have understood that a living organism is a collection of molecules that are undergoing all kinds of chemical reactions. And these molecules and these chemical reactions, they're just the same as the ones that are happening in non-living matter. We can, in a test tube, have these same molecules react in exactly the same way as they would inside your body. So what is it that makes these molecules alive in one case and not in the other case? It's because they form part of a whole. They form part of an organized whole. The organized whole, in this case, is an organism. That organism has the property of being alive. And I will not maybe discuss it here, but there are some definitions of what aliveness means at the level of a systemic whole. You can specify certain kind of properties of the whole that are not there in the parts, in the molecules. And then finally, a very simple example. What's a song? Song is something that has a melody, that has a harmony, that has a rhythm. If you write down the song as notes, each of these notes, a note does not have a melody, a note does not have a rhythm, a note does not have a harmony. It's by putting these notes together in a particular order that you get these emergent properties of harmony, rhythm, and melody. So this idea that the whole is more than the sum of the parts, it's in philosophy, it's often called holism. So holism is a little bit kind of the opposite of reductionism. Reductionism says, if you want to understand some complex thing, take it apart and look at each of the individual parts. Holism says, no, you should look at the whole they form. The elements are irrelevant, it's only the whole that counts. Now, both positions are kind of extreme and not very practical. So what we need really is we want to have the best of both worlds. We want to have an approach that looks both at the parts and at the whole and tries to find how the one leads to the other. And that approach is an approach known as systems theory. Systems theory, its original name, it's not really a theory, at least not a theory in the sense that we have something that makes particular predictions. Nowadays, it's more often called systems thinking, systems approach, systems research, systems science. So let's look at that system. Where does it come from? And one of the founders of systems theory was a biologist called Ludwig von Bertalanffy. And he started from a criticism of the Newtonian framework. So in the Newtonian framework, you look at objects that move according to certain laws. Typical example is a planet circulating around the sun. And basically, you know what the object is, you know what its speed, what its position is, you know the forces, you know everything. You are looking at what is known as a closed system. Everything you need to know is inside the system, so you can calculate exactly how the planet will rotate around the sun. But von Buitenland was a biologist, and in biology, if you look at an organism is not a closed system. An organism needs to take in things from its environment. It needs to breathe in oxygen, it needs food, it needs water, and it produces an output, it produces carbon dioxide, urine, etc. So living organisms cannot be closed off from their environment. If you put a living organism in a closed bottle, it will die. So that brought von Buitenland to the idea of now to define a system. And so he defined the system very simply as you have something with a boundary. That means you make a distinction between what's inside and what's outside of the system. Whatever is outside, you call the environment. Whatever is inside, you call the system. And you assume that those two are not separated. So the boundary is permeable. There are things that go in and there are things that go out. What goes in, you call input. What goes out, you call out. What are the things that go in and out? Things can be matter, like if I eat, I'm bringing food inside my own body. Can be energy, like in the case of the Bernard phenomenon. What I'm doing with that liquid, I'm adding energy by heating it. Or what can go in can be information. A computer will get information via the internet as its input. Yes?
Can you just make the boundary large enough that there's nothing outside?
You could do that, but then you would have the whole universe and nobody knows what's all in the universe. It would not be very useful. So, input and output. So, by example, so I already said my own body, I need input of food, of water, of oxygen that goes into my body. What comes out are the feces, the urine, the CO2, that's the output. If I look at the brain now as an information processing system, what comes into my brain are things I sense, things that I perceive to my ears, to my eyes. That's input. What I decide to do with the things I perceive, my decisions, my actions, that's the output. And then for a computer, well, computer, of course, there's input. For example, you get a file from the internet, and then the computer turns that file into a movie, which you then watch on your screen. The projection on the screen is the output. The information that comes from the internet is the input.
Is this the same thing as exporting entropy?
It does not need to be entropy. Entropy is one form of thing that you could export, that you could be in your output. In a dissipative structure, your output will typically have more entropy than your input, but that's not necessary. It could have the same amount of entropy.
Okay.
I mean, typically a computer will not add any entropy. If let's say I send you an email, input to your computer, and you forward that email to somebody else, output of your computer, the file is still the same. Nothing has been taken away from it. It has not become more entropic.
But it can also be more structured.
More what?
More structured.
It can also be more structured. Yes, you can also reduce the entropy. But let's not talk about that now here. Here we're just having a very simple notion of input and output. So input is any influence that makes something happen inside the system. And output is any influence that a system has on its environment. What happens in between? Typically, they use the term processing. Sometimes it's called throughput. That means the input is somehow processed into something else, and that becomes the output. So, for example, your computer may process some of the numbers that you put into it and process that into a picture. So systems, according to systems theory, it's a very abstract scheme, and that is the strength of it. We are not specifying what the system is. We're not specifying necessarily what the input is, what the output is. This is a very abstract universal scheme, can be applied to minds, can be applied to organisms, can be applied to machines, can be applied to planets, can be applied even to abstract systems. I could have an abstract system like software, where the software takes certain data, turns them into something else. It could even be something as abstract as a mathematical theory with which I make certain calculations. This is an extremely broad view. And that is why von Bertalanffy didn't just speak about systems theory, but about general systems theory. That means he tried to formulate a framework that would apply to any kind of system. Any kind of system, that means the substance, the material, does not bother. By making that abstraction, what's a big advantage? That is that now you can start comparing systems of different types and finding analogies, or as systems theorists would call it, isomorphism. That means there is a similarity in structure between one system and another system. For example, that's one of the most fruitful similarities is the similarity between a brain and the kind of neural networks that they use in AI. The brain gets an input of images. We see lots of images, and we start to learn that some of these images are cats and some of them are dogs. Well, you can do the same with the neural network on a computer. You give it lots of images, you tell it which ones are cats and which ones are dogs, and after a while, the neural network starts to recognize what are cats and what are dogs. So that's a very powerful idea that you can use your understanding of one type of system in order to understand another type of system. Another of these analogies that has been used by systems theorists. If you look at an organism, you know that it needs things like food, that food needs to enter the system, that food needs to be digested, that food needs to be converted into different kind of molecules, that these molecules are used to build muscles, to accumulate fat, to produce energy, etc. You know that the organism, in order to do that, needs all kinds of different systems, including a system that transports these molecules from one place to another, a circulatory system, which are our blood and our lymph vessels. Now you can apply the same to a city. A city also needs input. It needs to get food and material from the outside. That food needs to enter the city. That food, or that material needs to enter the city. That material needs to be processed. There will be factories that take that material, process it into something else. They process it into goods. These goods need to be transported, so there must be a circulatory system, which is the equivalent of the traffic network. Some of those goods need to be stored, so there must be an equivalent of storage systems. And there is one particular type of systems theory called living systems theory that uses this analogy very explicitly and saying an organism is a living system, but a city is also a living system, or a factory, or a country. All of these need to have all these different functions in there.
So, living system theory is based on the functions that the general system needs to have, like food, water, export of waste.
Well, not the general system, but the general system that is in this case called a system, a living system. There are simpler systems that do not have all these functions. But once a system has a certain degree of complexity, you can say it needs to have all these subsystems, all these structures. So, yes?
Do all living systems include like some form of living organism within them, or could we have entirely inorganic living systems at a certain level of complexity?
In theory, yes. Yeah. Yeah. So the dream of von Bertalanffy is to create these really general systems here. That means this theory that describes systems of any type. And that by looking at the whole they form, and the whole they form is because systems are connected. So now we need to go to the next step in understanding a system, and that is coupling. So we know that each system has at least an input and an output. But now that means that the output of A can be the input of B. So coupling between systems means you take part of the output of one system and somehow use it as input for another system. But let's look at the different forms of coupling, and these are the three simplest type of coupling. We assume that we have only two systems. How can you couple them? That's the simplest way, sequential. The output of A is simply the input of B. It's a sequence. They are just on a line. I can also have parallel coupling. That means that they take input from the same source and they give output to the same source. So they are working in parallel. They're kind of doing similar things. They're using the same kind of resources and they're producing the same kind of waste. And then I can have the circular one, which is that the output of A is again B, but the output of B goes back to A. So I have three types of elementary couplings between two systems. But now, if I take several systems, the number of potential couplings is as complex as I want. So a general system can be seen as a network of subsystems. So each of these small systems is a system, each of these small ones is a system. Altogether, they form one bigger system. So this is, you might say, that is the essential idea of systems theory. Every system consists of a network of subsystems. Every system is itself part of a network of bigger systems. Yeah.
Isn't that a bit of the same thinking than reduction in the end then? Because you can reduce to the smallest system?
No, because you can't reduce. Reducing would mean that you look at each of these separately. What system says it's the network that counts. So what you see here is the individual systems. I make some random links. What reductionism would say, forget about all these, look at each of these separately. System theory says, doesn't matter what's inside these little circles here. What counts is the network of connections. So that is the essential idea. You start looking at the couplings, at the connections. It's because of the network of connections that we can say, well, that thing there could represent an organism, but it could potentially also represent a factory, or it could represent a city. They have a similar structure. So now we come to the next important idea, that is that in systems theory, you can go up towards larger systems called the supersystems, or you can go down towards smaller systems, the subsystems. So if I look at, for example, at the level of individual people, each of these individual people consists of subsystems which are organs that are connected in various ways. The organs of my body are all coupled with each other. these organs consist of cells, these cells consist of molecules, but I can also go up. I can say I, as an individual, am part of the system VUB, which is part of the system Flanders, which is part of the system Belgium, which is part of the system European Union, which is part of the system Earth, which is part of the solar system. I can go up as much as I want, and I can go down as much as I want. So in systems theory, to understand the system, you need at least to go one level down and one level up. The going down, that's a reductionist strategy, looking at what's inside. The going up, that's a holistic strategy, saying it's just part of this larger whole. So to get a little bit more detail, here we start from the atom, but we could have gone even lower. We could have gone to the elementary particles, atoms for molecules, for macromolecules, macromolecules from organelles, which are parts of the cell, from cells, from tissues, from organs, organ systems, from organisms, from social systems, from larger social systems, etc. So you can go up and down as much as you want. So it's kind of like zooming in or zooming out, like on Google Earth or on Google Maps. You can zoom in to the level of a single house, or you can zoom out until you see the whole planet. And the level of zoom, you choose it, but typically to understand, for example, if you want to know something about, let's say, a particular city that you want to visit, you may want to zoom in on some parts of the city, like musea or statues or cathedrals, but you also will zoom out to see what is the city connected to, what are the things around it. So that's the systems theory approach. You move in what's called the scale dimension. You go up or you go down. You zoom out or you zoom in. You look at the smaller parts, but you look also at the larger wholes. So in medicine, it's a typical philosophical discussion. Most traditional medicine, Western medicine, is reductionistic. If you're ill, first you try to find out which organ is the problem, and then in that organ, what precise molecules maybe are not doing what they should. So which particular drug, that means a particular molecule, can we give that will affect that particular cell type in that particular organ to solve your disease. But then you have more holistic or systemic approaches that say, well, our body isn't just a collection of organs or a collection of cells or a collection of molecules. All these organs work together, and if one organ isn't working well together with another organ, that may affect a third organ, which make you feel tired in particular situations, and by being tired in this particular situation, you may not succeed well in your job, and therefore you may get unemployed, and that will cause a stress that will affect other organs. That's the systems approach. You look at all these different levels and how they interact. But of course, the disadvantage is it makes it much more complicated, because you don't know necessarily at what level the problems that you want to solve are situated. Holistic medicine sounds good. In practice, it's not obvious where you start, because there are so many different subsystems and supersystems that may affect your health. So that's another picture that I made. Going down, that's reductionistic strategy, looking at the parts of the parts of the parts. Going up, that's a holistic strategy, looking at the larger wholes. But the systems approach is the ability to move up and down at the same time. That is also a notion that we will also encounter many times. It's called a hierarchy. So the hierarchy of systems and subsystems. The higher level, to some degree, controls what happens on the lower level. But on the other hand, the lower level also has some effect on the higher level. So you have these both up and down effects. And there is a term for that. It's not, I haven't mentioned it in the lecture notes because it's a bit, gets a bit more complicated. But there's a notion of downward causation. The reductionist strategy says, if you want to understand how a system works, look at the parts, write down the laws that describe the parts, and you will know everything. The whole kind of is controlled, is determined by the parts. The notion of downward causation says, no, that's not enough. The whole also influences the parts. The whole puts certain constraints on the parts. Let me give you one example. I am part of the VUB, I'm paid by the VUB. That means that I'm supposed to do certain things, like, for example, at this moment, be teaching this particular course here. Suppose that somebody would want to understand how I function and would look at my brain in every detail and try to find out how I function. From looking at all the molecules of my brain, you would not be able to predict that at this particular moment I will be teaching in this particular room for this particular course. But on the other hand, if you know the super system to which I belong, namely the VUB, you will find that I am a subsystem of the VUB and that I am a teacher that gives that course in that hour, in that room. That's because the super system VUB is downwardly causing me to give this lecture. I don't have the choice of, I mean, maybe this morning I might have thought, well, 4 o'clock in the afternoon, that's not my favorite moment. I would rather give the course at 5. No, I don't have that freedom. The super system VUB has decided that this course should be at 4 o'clock. So the super system downwardly causes me to give this course specifically at this place, at this time. Yeah.
So can you apply that same thought? Because you can go up and down levels of perception, right? Like a framing. So you can look at the view of society, the individual, the organs, and so on and so on. But also, like the decision to look at things from a particular level of framing, that's also distributed. Is also kind of what you're saying. Because, so for example, it could be that the decision to look at from a certain framing is coming from the level of society, or it could be that it's coming from yourself or your peers, or it could be that you could think of it coming from a particular region of your brain, or that it's telling you to think that way, or it could be that it's coming from your stomach telling you you have to go to the refectory now. So it's also interesting that the decision, like at which scale at which you view things, is also scaled. Like you also can't position that decision even at the level of the individual.
No, exactly. To understand how a system behaves, it's not sufficient to know how each of its components behave. You have to look at the different levels, and some decisions are made at the higher level. For example, the decision that I would teach in this room at this moment is made at the level of the faculty of the VUB. On the other hand, the fact that now I just went to get a drink, that was my body that had decided that it was so hot here that I needed some water, so you can understand it at the level of my physiology. But then the fact that I'm telling you this particular example is because I, at that moment, at the level of my brain, has made a decision that that would be a good example. So each of these decisions is made at a different level. Yeah.
But can't you actually know everything from one system? Because just as you said, you do get the input from the over system into your system. So that input that is needed to know about the influence of the other system is in the system. So you can.
But it enters the system, but that's not enough. Let's go back to this example of the little magnets. Each magnet on its own is kind of free to move, But the moment that the other magnets have decided to align in a particular direction, that freedom of movement is very much reduced because the magnetic field of these other magnets has become so strong that this little magnet has lost its freedom to move. It's not really that it's inside the magnet. It's the field around it. The field around it creates a constraint. It's a term we will see later. It's a very important term, the term constraint. A constraint is something that limits the freedom of the system. A constraint says the system can move here and here, but not there. There is a limit to what it can do.
And is the relation between subsystems, systems, and supersystems always in a hierarchy, or can you also think of non-hierarchic system orders?
That's an interesting and controversial discussion. There are, of course, all kinds of non-hierarchical effects, but the reason to use this kind of hierarchical representation is that at least it creates some simplicity in this complexity. But if I would look, for example, here, well, that digestive system, I can't quite say whether the stomach is more important than the intestine or than the liver. There are both hierarchical and non-hierarchical couplings and dependencies, of course. That's part of what complexity is. But the hierarchical part is at least simple enough that you can make some abstraction and say, well, I can distinguish these different levels, and that gives me some kind of a grip. Because that's one of the disadvantages of the holism. If you would be a strict holist and say, it's only the whole that counts, well, what is the whole? The whole is the universe. That means everything is connected with everything. Where do I start? I'm feeling bad. Is it because of the position of a star in the Andromeda galaxy that I'm feeling bad? Is it because I haven't eaten enough? Very reductionistic explanation. Is it because the VUB is expecting me to do things that I don't really want to do? That would be a kind of a higher order explanation. If you become too holistic and you say everything interacts with everything, then you don't know where to start anymore. So then it becomes useful to draw boundaries, and that is, you might say, the simplification that systems theory does. It says draw a boundary, but what systems theory also say, there is generally more than one way to draw a boundary. Boundaries are not objectively given. In some cases, like with a cell has a membrane, it's a very obvious boundary. But suppose that now I look at something like a fungus. A fungus has a mycelium, which is kind of a network of cells that spread throughout the organic matter in the soil. Where does the mycelium start? Where does the mycelium end? There is no clear boundary. System theories are aware of that, and that's why they say you draw a boundary, but you draw a boundary because you want to solve a particular problem. That means you want to pay attention to certain aspects, and you necessarily cannot pay attention to all aspects, so you make a simplification. Yeah.
Can boundaries and systems overlap? For example, let's say you taught at both UB and a different university, you would essentially be part of two different systems.
Yes, exactly. I'll give that example later in the course. It's less common, but yes, a system can belong to more than one super system. So the simple view of the hierarchy is this one. It's called a tree structure. Imagine that you put that upside down, then you get the structure that looks like this. So it looks like a tree. So a tree is mathematically defined as this kind of structure. But sometimes there are crosslinks. In real trees, you can't have crosslinks. But a crosslink would in this case mean you have a system that belongs to more than one super system, and yes, I belong to the system VUB, but I'm also a member of a particular judo club, and I'm also an inhabitant of the city of Vilvoorde, So I belong to the system Vilverde, I belong to the system VUB, I belong to the system Budokan. Yeah, I do belong to more than one system. Okay, we have just enough time to start the next chapter on cybernetics. Cybernetics and systems theory are two related approaches, and often, if you go to conferences, you will hear the two together. Some of the conferences in domains are called cybernetics and systems, or systems and cybernetics. So systems theory and cybernetics have a history that overlaps. They both kind of emerged around the 1950s. They both were looking for a theory to explain how more complex systems like organisms function. They both were at a level of abstraction where they were not looking at what is the exact material out of which a system is built. So they both were looking at abstract structures, organizations. What's the difference? System theory has been focusing on the structure of a system. So the structure of the system that was this kind of way, what the structure is, the way how all the different components are interconnected. That's the structure. Cybernetics looks at the function of the system. The function of the system is what is the system doing? What is it for? What does the system try to achieve? Now, if we're looking at physical systems like planets, that's a meaningless question. The planet just turns around the sun because there is gravity. The planet doesn't have any choice. But if you look at living systems, at social systems, firms, organizations, robots, they are goal-directed. Goal-directed is what is that goal-directedness? Goal-directedness is, starting from a Newtonian point of view, something very mysterious. Because the Newtonian worldview is deterministic. It assumes that the future is determined by the past. That means if you know, like here, the situation at this point in time, you can draw the trajectory and you know what the system will be. As I said here, in practice, it's not that easy to predict, but in principle, determinism says if you know this, then you know this. So the future is determined by the past. But what is goal-directedness? Goal-directedness means that you are acting towards a future state, towards a goal that is not yet there. So how can that be? So Aristotle already made a bit of an analysis of that, and he was speaking about different types of causes, which I'm not going to repeat here. But one of the causes he spoke about was what he called the final cause. So the final cause is the situation in the future to which you are acting towards. So there is the goal. So that is the idea of the trajectory. In the past, I'm at this state, I follow this trajectory. That's what the reductionistic Newtonian view would say. But then I go towards the goal, and according to Aristotle, that goal would somehow cause me to act in that. So, from the Newtonian point of view, that's paradoxical. The future cannot influence the present. Now, what cybernetics did, it solved that problem. That means it gave a very simple explanation of how a system can be goal-directed without contradicting the notion of causality. So how did cybernetics do that? By introducing something that you might call circular causality. And circular causality corresponds to this idea that we already saw in systems theory, circular coupling. Circular coupling means you take some of the output of a system and you bring it back as input of that same system. So what does it mean in practice? Something like this. Imagine that I have a camera. The camera is taking a picture, and it is sending that picture to a screen, and the picture that the camera sees is shown on the screen. Now, what happens if you point the camera at your own screen? So, for example, here is a camera that Orion is using. Suppose that his computer was showing the image that the camera sees, and then he points it at the screen. What do you see? It's kind of a paradoxical idea. So you can try to do the experiment, but typically what you see is some kind of abstract patterns appearing that can be understood as a kind of a self-organization. So what you're doing here is you're taking the result of a process, the output, the effects, you're bringing it back to be the input, that means the cause, that means the thing that gets in. And if input is the same as output, yeah, something happens. It may look paradoxical, but it's very easy to do. And if you look around in the real world, you will see that there are plenty of cases where systems have circular couplings. That means that some of their output becomes input again. So that is the idea that brought up this whole field of cybernetics, circular causality. And then in the next lecture, we will look at the notion of feedback, which is a way to understand this idea of circular causality, and in particular, how feedback can help us to understand goal-directed behavior. So, in essence, cybernetics is a science of circular processes, things that point back to their own entry, and that, even though it seems paradoxical, it allows you to explain a lot of things, and in particular, it allows you to explain how systems can be goal-directed without having to assume that the goal in the future influences something in the present. Okay, that will be done for next week.
Are you going to use philosophy?